Hello students, welcome back. Let us resume our discussion in section 2. The fundamental theorem of calculus says the definite integral of a continuous function in a closed and bounded interval a to b can be calculated as a net change of the antiderivative function. And yes, the antiderivative always exists. There are infinitely many antiderivatives out there because of the integral constant plus c, but you don't have to worry about it. They're going to cancel out anyway as we take this net change. So you don't have to consider plus c. And then we went through some exercises associated to those computations. There's more. And I gave you a hint, not directly related to fundamental theorem. Well, they're related, but not directly to the fundamental theorem. And as you can see here, well, how do you calculate the antiderivative here? Let's see, I'm gonna need some space. No, I'll be bigger font. X squared sine of x over log of 1 plus x squared dx. Any idea how to calculate antiderivative? Another one here, square root of 4 minus x squared dx. How am I going to calculate antiderivative here? If it is 4 minus x, then it's not too bad, you see. And we have a linear expression, ax plus b, inside the power function. So we can use this to find the antiderivative. You see, k power is 1/2 power. All I need is extra 1 over a, but look at this. X squared, not ax plus b, so this is much harder. How about the next? We have absolute value sign. Well, all those are related to graphs, as a matter of fact. This one here, if I plot a graph, then things will look pretty self-sufficient. Let me show the graph. So x squared sine of x, and then I'm going to divide it by log of 1 plus x squared. And then I'm going to plot it from -2 to +2. And then don't pay too much attention to all those mathematical codes. Just look at the graph. What do you see? We have positive area here and negative area there, canceling each other out, and just 0. Do you see that? Negative to +2, and then we have an odd function. So positive part, negative part cancel each other out, and you end up with 0. Without the graph, it's going to be a bit harder, but you can still see that this is an odd function. X squared is even, x squared is even, 1 plus x squared is even, log of that, again, even. Sine of x is odd. So we have symmetry with respect to 0. And then going from -a to +a. But of course, graphing would be very helpful here. Speaking of a graph, how about this? And they're plotting from -2 to +2. We have a circle. As a matter of fact, Yeah, that's adjusting the viewpoint and an aspect ratio to true scale actually helps. And what do we see? We have a circle. Exactly not a circle, actually half a circle. So the area is gonna be half of area of the circle. So this is gonna be 1/2 pi, and then what's the radius? Let's put some space there as well. And then that is what? 4 pi divided by 2. We can answer like this. Is there any analytical way to calculate this? Yes, there is, but that's something we are going to do in calculus 2. Here, let's just focus upon the geometry. This is a circle, a semicircle, half circle, centered at the origin with radius 2. So area of the semicircle, area inside the semicircle is half of pi r squared. Okay, how about the next problem here? Well, again, let's use the graphical method. So absolute value of sine of x, and then going from 0 to 3 pi over 2. Okay, here's a graph, and here true scale is a bit too squished. Okay, all right, about that. Does it help? Well, if you compare that with the graph of sine function, not absolute value, just sine function, then something may click. You see, if you look at just a sine function without the absolute value, we have some cancellation here, positive, negative canceling out. But if you take absolute value, this one stays the same, but that part comes up. So we have a bit different integral. Now, as for the area of a sine function, well, we can use the fundamental theorem to figure out. So we're going to handle this way. Instead of trying to calculate this one with the absolute value, we don't need these anymore. I'm going to divide this interval into 2. 0 to pi, and then pi to 3 pi over 2. And then there's a 3 pi over 2. And then from 0 to pi, sine function is positive. So we do not need this absolute value. Just sine of x is just totally fine. And then here, in the second interval, sine is negative. So if you take the absolute value, we get extra negative. Or you can push this negative outside and write like this. Oops. Okay, that's better. And then as for these computations, using fundamental theorem here and fundamental theorem there, it's not going to be too bad. Antiderivative of sine is negative cosine. And then that's running from 0 to pi. And then this one, antiderivative of sine is negative cosine. And that's going from pi to 3 pi over 2. And all you have to do is this computation. Let's see. Plug in pi. Cosine of pi is actually -1, so negative of -1, so positive. And then minus cosine of 0 is 1, so -1, so negative of negative, so we have positive. And then cosine of 3 pi over 2 is 0, so 0. And then cosine of pi is -1, and we have negative here, positive, and another negative here, so you're gonna end up with 3. Probably better written as this way. Yeah, sign can be a little bit tricky, but if you be careful, if you just calculate the antiderivative through just sine function and apply the fundamental theorem, you're going to get just 1. By the way, here in the answer key, I gave you the graphical presentation too. Red is absolute value of sine of x, and then this light blue is sine of x going down. So with sine of x function, this part here and that part just canceling out, so we get something smaller. And then for absolute value, no cancellation, you have to add them all. And you see the first part, and then what I'm talking about is this. Okay, yeah, like this. And then this part, and that part, we have cancellation for sine function. But for absolute value of sine function, no cancellation like that. So what actually happens is only the area of this part here, and then multiply by 3. You see this one, and that's this cancellation, versus this one repeated twice more. And this interval turns out to be 1, so no surprise we get 3 versus just 1. All right. We went through some exceptional problems. Odd function and by symmetry becoming 0. Okay, that was a bit unusual. The kind of problem that you had to rely upon geometry, that too is rather unusual. The one associated with absolute value, this type of problem is not unusual at all. It's pretty common. You have to deal with those. And how do you deal with that? There can be many ways, but the most standard way will be to separate the domain, separate the interval, and then calculate the definite integral separately and apply the fundamental theorem separately. And of course, graphical justification always helps. So plotting is always encouraged. All right, we went through some standard and some non-standard problems on the calculation of the definite integrals using the fundamental theorem of calculus.